Welcome to the deep dive. I want you to picture something for a second. You sit down at your laptop, you type this really complex prompt into your favorite AI tool,
Yeah.
and you hit enter.
Right, something we all do every day.
Exactly. Now, what if the server doing the heavy lifting to answer that prompt isn't, sitting in some massive water-guzzling warehouse in the Nevada desert?
Oh, yeah.
What if instead your prompt is actually beamed up and processed by a server orbiting hundreds of miles above your head, like silently gliding through the freezing vacuum of space?
I mean, it sounds like pure science fiction, honestly.
Right.
But looking at the intelligence we've gathered today, putting the cloud in orbit is, well, it's rapidly becoming a matter of strict economic and physical necessity.
Yeah, and that is exactly our mission for this deep dive. We are combing through a pretty massive stack of sources today to figure out if orbital data centers or ODCs are just this wild pipe dream or an impending $39 billion reality.
It's a huge stack, yeah.
Yeah, it really is. We're pulling from a comprehensive strategic analysis presentation on ODCs, some internal test results from Google Research, the European Space Agency's latest space environment report, and some very heavy legal analysis from Morgan Lewis.
Plus, we've got the latest press releases from these pioneering space startups, right? Like Axioma Space, Aetherflux, StarCloud, and Orbit AI.
Right, to see how the industry is actually trying to, physically build this stuff.
It is a fascinating stack to synthesize. Because to understand it, you really have to look at how computer science fundamentally clashes with astrophysics.
And then the lawyers get involved.
Exactly. How all of that physical hardware then gets tangled up in international law.
Okay, so let's unpack this. Before we can look up at space, we actually have to look down at Earth, specifically, why Earth's infrastructure is suddenly failing us.
Right.
The whole catalyst for this massive shift off planet is AI's completely insatiable appetite. I mean, we tend to think of the cloud as this invisible, weightless thing floating around our devices, right?
Yeah, but the physical reality of the cloud is incredibly heavy, especially with the explosive growth of generative AI over the last few years.
Right. It's not weightless at all.
No, it is grounded in thousands of tons of steel, concrete, electricity, and water.
And the sources paint a pretty grim picture of our earthly constraints right now. We are looking at severe power grid overloads across major tech hubs. We're looking at massive water depletion just to keep these AI server farms from literally melting down. And the land consumption is just skyrocketing.
There's a really sobering quote in our materials from Travis Beals at Google about exactly this.
Oh, right. The one about the expansion.
Yeah. He notes that if AI usage keeps growing at its current pace, we are facing the possibility of, quote, unimaginable expansion.
Unimaginable expansion. That's terrifying.
It is, and that expansion hits a literal brick wall when you factor in terrestrial construction timelines. According to the strategic analysis, building a traditional data center down here takes anywhere from 5 to 8 years.
Wow, 5 to 8 years.
Yeah, because you have to acquire the land, you battle through zoning permits, you do the physical construction, and most importantly, you have to wait in a massive queue to secure the necessary power grid connections.
So wait, the AI industry is iterating on models in a matter of months.
Right.
But the concrete and steel infrastructure required to run them is moving at a snail's pace. The Earth is literally running out of easily accessible resources to sustain this localized growth.
Exactly.
But, okay, let me play devil's advocate here. If the infrastructure is so incredibly heavy and takes so much concrete and steel, blasting all that metal into space sounds absurdly expensive.
I mean, it historically has been, yeah.
Right. Even just sending a few astronauts up costs a fortune. So how does putting thousands of pounds of server racks on a rocket actually solve an economic problem?
Well, historically, it wouldn't have. But that math has fundamentally changed. And it all comes down to the absolute collapse of launch costs over the last decade. The historical data in our sources maps this beautifully. During the Apollo era, the 1960s, it cost well over $1,000 to put a single kilogram of payload into space.
$1,000 for 1 kilo.
Right. And the space shuttle didn't dramatically change that math for commercial viability. Even the early Falcon 9 rockets in the 2010s were just starting to, bend the curve.
But the real inflection point, according to the analysis, is SpaceX's Starship.
Exactly. The strategic analysis identifies this very specific economic threshold, which is $100 per kilogram.
$100, that's a tenth of the Apollo cost.
Yep. Once the launch cost drops below that $100 mark, which is the ultimate design goal of Starship in competing heavy lift vehicles, putting heavy server racks into orbit, crosses a critical line.
Right.
It goes from being a billionaire's vanity project to a highly lucrative, commercially viable business strategy.
I have to admit, I was really struggling with this concept initially. Even at $100 a kilo, a rocket launch is a massive capital expenditure compared to, like, just buying an empty warehouse in Ohio.
Sure.
But then I started thinking about it like moving out of a cramped, hyper-expensive city like San Francisco or New York
Okay.
and moving to a completely off-grid cabin in the woods, hiring the specialized moving van to haul all your stuff out to the middle of nowhere. That costs a fortune up front.
Oh, I see where you're going.
Right. But once you are finally there, your rent and your utilities are literally zero for the rest of your life.
That analogy gets right to the heart of the business model. In space, the utilities are what make the economics suddenly tip in favor of orbit.
Yeah.
When you remove the terrestrial constraints of power generation, the operational advantages become staggering.
The sun-drenched cloud. Let's talk about power, because the numbers here honestly broke my brain for a minute.
They are wild. The key is putting these data centers into what's called a sun-synchronous orbit.
Okay, explain how that works to me. Because I always assume satellites just went around the Earth and experienced day and night like we do.
Most of them do, yeah. But a sun-synchronous orbit is a very specific path that travels roughly from pole to pole.
Yeah.
By calculating the exact altitude and angle, the satellite orbits the Earth at the exact same rate that the Earth revolves around the sun.
Oh, wow.
Yeah. The practical result is that the satellite is perpetually riding the Terminator line, that twilight edge between day and night.
Right, right.
Because it never crosses into the Earth's shadow. Your solar panels have near 24/7, 365-day access to pure sunlight.
And there are no clouds?
No clouds, no weather systems, and no atmospheric gases scattering the light before it hits the panels.
The Google research source noted that because of this lack of atmospheric interference, solar panels in orbit are up to 8 times more efficient than the exact same panels down here on the ground.
8 times. It's
Yeah.
incredible.
8 times. Plus, you completely eliminate the need for those massive, heavy lithium-ion battery banks that terrestrial solar farms use, right? Because they need to store power for the night.
Exactly. And up there, night never comes. You're tapping into an infinite, clean, zero-carbon energy source.
That's just wild.
When you factor in the lifespan of a server drawing free energy, the cost collapse is breathtaking.
And the startup projections really reflect that. StarCloud, which was founded by ex-SpaceX engineers, they estimate that the total energy costs in space could be 1/10 of Earth's energy costs.
Wow.
And that calculation includes the upfront cost of launching the hardware. Another company, Lone Star, is targeting an operational cost of 0.1 cents per kilowatt hour.
It's basically free at that point.
Right, and you are completely freeing up Earth's resources. You aren't straining the local power grid or draining the local reservoir just to train a chatbot.
Which is huge.
Yeah.
But cheap power is incredibly appealing, but it's only like half of the operational advantage.
Okay, what's the other half?
The other half solves one of the biggest bottlenecks in modern space operations. The industry refers to it as orbital edge computing.
Okay, so instead of just storing data, they are actually processing it on the edge of the network, like right there in space.
Exactly. Think about the sheer volume of data we currently generate in space. We have thousands of Earth observation satellites constantly taking high-resolution optical images, radar scans, hyperspectral weather data.
Right.
Right now, all of that raw data has to be beamed back down to Earth ground stations to be processed.
Which creates that massive downlink bottleneck I was reading about.
Yeah.
We are generating way more data up there than our radio antennas can quickly download. It takes time, bandwidth is incredibly limited, and the latency is super high.
But if the processing power is already floating in orbit right next to the observation satellite, you bypass the bottleneck entirely.
Oh, that makes so much sense.
You can use high-speed optical laser links to shoot the raw data directly from the camera satellite to the orbital data center. Axiom Space uses a specific military and intelligence acronym in their press release to describe this capability. It's called PED.
PED, what does that stand for?
It stands for Process, Exploit, and Disseminate.
So instead of sending a terabyte of raw, cloudy images down to a ground station, The AI on the orbital data center processes all those images right there in space.
Right.
It finds the exact insight you are looking for. Maybe it spots a specific illicit shipping vessel moving in a harbor, or, I don't know, the thermal signature of a wildfire just breaking out.
And then it beams just that tiny, highly valuable alert, maybe just a few kilobytes of text and coordinates down to Earth in real time.
Yeah.
The latency practically drops to zero.
It's brilliant. And beyond the speed, the sources point out an ultimate physical security advantage, too.
Oh, absolutely.
An ODC is fundamentally immune to earthly threats. No earthquakes, no floods, no local power grid failures from a winter storm. It's completely isolated from terrestrial geopolitical conflicts or physical sabotage.
Yeah, nobody is cutting a fiber optic cable in orbit.
Exactly. For governments or massive financial institutions, having your data physically orbiting in the vacuum of space is the ultimate disaster recovery backup.
It really paints a picture of an absolute utopia for cloud architecture.
Which naturally makes me suspicious.
As it should.
Right. If the energy is practically free, it's totally green, the latency for satellite data is eliminated, and the physical security is flawless. Why on earth hasn't Amazon or Microsoft already launched their entire cloud infrastructure into orbit?
Well, because space is, unequivocally, a hostile work environment.
Oh, here we go.
This is where the excitement of computer science slams headfirst into the unforgiving physical reality of astrophysics.
The physics constraint. Bring us back down to reality. What's the main issue?
The most fascinating roadblock is thermal physics. Most people naturally assume that because space is incredibly cold-like, it's a freezing vacuum. Cooling a hot computer server up there should be effortless.
That is 100% what I assumed. It's a freezing vacuum. You just crack a window, let the cold vacuum in, and the server cools down instantly.
Yeah, but the vacuum is actually the core of the problem. On Earth, we cool data centers using two primarily physical mechanisms: convection and conduction.
Okay.
Convection relies on using fans to blow cold air over hot components, which carries the heat away. Conduction involves using liquid cooling loops to transfer heat into water, which is then pumped out to cooling towers.
Right, like a radiator in a car.
Exactly. But both of those methods completely rely on having an ambient environment, an atmosphere, or a water supply to dump the heat into.
Oh, but a vacuum, by definition, is completely empty. There's no air to blow around.
In the vacuum of space, convection and conduction are impossible. You only have one single method of heat transfer left, and that's thermal radiation. You literally have to radiate the heat away as infrared light.
Okay.
And this process is strictly governed by a very unforgiving physical law called the Stefan-Boltzmann law.
Yeah, I saw that formula in the strategic analysis, and it looked completely intimidating. Q equals epsilon sigma AT to the fourth power.
It looks scary, but you don't need a physics degree to understand the grim reality of that equation. It essentially dictates that the amount of heat you can radiate away into space is limited entirely by your surface area and your temperature.
Right.
Down here on Earth, if a server gets too hot, you just spin the fans faster. In space, if your server gets too hot, you literally have to build a bigger physical radiator panel to increase your surface area. There is no other workaround.
Okay, let me synthesize this because this completely flips my understanding of space. Because space is a vacuum with no air to carry heat away, putting a high-powered AI server up there is actually like trying to run a high-end overclocked gaming PC inside a giant, perfectly sealed thermos.
Yes.
The heat generates inside, but it has absolutely nowhere to go.
That is a phenomenal way to visualize the thermal trap. And because of this limitation, orbital data centers suffer from a massive density deficit.
Glad density deficit.
Yeah, down on Earth, a modern AI server rack in a liquid-cooled facility can easily draw anywhere from 30 to well over 100 kilowatts of power, just packed tightly together.
But because of the thermos effect, what can an orbital rack handle?
An orbital rack caps out around 10 to 20 kilowatts.
Oh, wow. That's a huge drop.
It is. That thermal management limit acts as an absolute unbreakable ceiling on your performance. You physically cannot pack the servers as densely in space as you can on Earth. Otherwise, they will literally melt themselves into slag.
That is a massive constraint. And heat is just the first hurdle, right?
Yeah.
The sources also highlight two other massive physical threats up there: cosmic radiation and space junk.
Yeah, it gets worse. Once you leave the protective bubble of Earth's atmosphere and its magnetic field, you are constantly bombarded by high-energy cosmic rays and solar flares.
Right.
When one of these high-energy particles strikes a silicon computer chip, it causes a phenomenon known as a single-event upset.
It can literally strike the chip, flip a 1 to a 0, and corrupt your data instantly, right? Or worse, just physically fry the component.
Exactly. And the traditional aerospace solution to this is rad hardening. You use specialized materials, redundant circuits, and heavy physical shielding to protect the chips.
Okay, that makes sense.
But the strategic analysis points out a fatal flaw for AI applications here. Because the exhaustive testing and physical redesign of rad-hardened chips takes so much time, they're usually 5 to 10 years behind the commercial processors we use on Earth.
Ah, I see.
If you are trying to train a cutting-edge generative AI model, you cannot remain competitive using processors from a decade ago.
That seems like an unsolvable tension point, which actually makes that detail from the Google research paper so interesting.
Right, the proton beam test.
Yeah. Google obviously didn't want to fly 10-year-old chips, so they took one of their modern Trillium TPUs, their custom-built AI processors, and they literally shot it with a 67 mega electron volt proton beam in a laboratory.
They just blasted this modern chip with intense radiation.
And the results were highly promising. They proved the commercial chip could survive approximately 3 times the radiation dose of a standard 5-year space mission.
Which is huge. It proves that we might not need physically ancient rad-hardened chips. We might be able to use commercial off-the-shelf components combined with really smart software that constantly checks for errors to survive the radiation.
But taking a successful lab test and operationalizing it at scale is still a massive challenge.
Very true.
And then we have to talk about the traffic up there, the debris.
Yeah, the European Space Agency's 2025 Space Environment Report does not mince words regarding orbital debris. They are currently tracking about 40,000 pieces of space junk.
40,000 sounds somewhat manageable in the vastness of orbit, honestly.
It does, until you realize those are just the pieces large enough to track with radar. The ESA estimates there are over 1.2 million pieces of debris larger than 1 centimeter blindly orbiting the Earth right now.
1.2 million.
Oh.
And because things in orbit are moving at around 17,500 miles an hour, a 1 centimeter fleck of paint or a stray bolt hits a satellite with the kinetic energy of a bowling ball dropped from an airplane.
It's devastating. The ESA report explicitly highlights the terrifying risk of Kessler syndrome.
Remind me what that is.
That's a theoretical cascading scenario where one accidental collision creates a massive cloud of shrapnel. That shrapnel then hits other satellites, creating more shrapnel, triggering a runaway chain reaction that could render entire orbital lanes completely unusable for generations.
Yeah.
If you are investing billions of dollars to build an orbital data center, a single rogue screw from a defunct 1970s weather satellite could destroy your entire investment in a microsecond.
So to protect against that, you need heavy physical shielding.
Right, which drives up the weight, which instantly threatens to push your launch costs back above that critical $100 per kilogram threshold we talked about earlier.
Okay, so let's look at the board here. We have this incredible promise-free energy, total physical security, zero latency for satellite data. But it's locked behind a brutal wall of thermal limits, proton beams, and high-speed shrapnel.
A very expensive wall, yes.
Because they cannot pack the server racks as densely as terrestrial data centers, they simply cannot function as a generic one-to-one replacement for Amazon Web Services or Microsoft Azure.
The strategic analysis makes that abundantly clear. Orbital data centers cannot compete on pure computational density. Therefore, the entire industry has to pivot.
Right.
They have to find highly specific, lucrative niches where their unique advantages outweigh the extreme physical constraints.
If they can't be everything to everyone, they have to target customers who care deeply about isolation, edge computing, or free energy, and don't care as much about raw server density.
Exactly. And the analysis outlines 4 specific sweet spot markets that fit this profile.
Okay, what are they?
The first is the one we touched on earlier, Earth observation data processing, solving that massive downlink bottleneck for satellite companies by providing orbital edge computing.
Yep, the PED process. The second makes perfect sense to me. National security and defense.
Oh, definitely.
If you are running military operations, having a physically isolated data center that can instantly process threat detection data in real time, completely beyond the reach of terrestrial missiles or sabotage, is invaluable.
It's the ultimate high ground. The third niche is highly specialized large-scale AI training.
Okay.
Consider an AI model that takes months to train and requires exorbitant amounts of power. You can tap into that infinite clean solar energy in orbit to train it. Even if the processing takes a little longer due to the density limits, you are trading time for completely free energy.
which could be worth it for these massive tech companies. And the fourth niche is that ultimate disaster recovery application, right? It serves as the absolute last line of defense for critical financial or governmental data against any terrestrial catastrophe.
Exactly. Securing those customers provides the financial justification.
Yeah.
But there is one final massive hurdle that the sources highlight, and it has absolutely nothing to do with physics or rockets.
Oh, this is the human problem.
Yes, it is entirely a human problem.
The legal chaos. This was the most surprising part of the Morgan Lewis analysis for me. The legal framework governing space was predominantly written during the Cold War, right, in the 1960s.
Yeah, the Outer Space Treaty.
It is woefully unprepared for modern cloud computing. The issue of data sovereignty is an absolute nightmare.
It really is.
Mm-hmm.
Let's play out a scenario. According to the foundational Outer Space Treaty of 1967, legal jurisdiction over a space object belongs to the launching state.
Okay.
So if a U.S.-based company launches an orbital data center on a U.S.-built rocket, U.S. law applies to the physical hardware of that satellite.
But data privacy laws are fiercely territorial. Take the European Union's GDPR, for example. It heavily dictates where data can physically reside and how it can be accessed based on the citizenship of the user and the location of the server.
Exactly. So imagine a massive enterprise company hosts sensitive European customer data on this U.S.-launched satellite. A government entity down on Earth issues a subpoena to seize that specific set of data.
But the physical server holding that data is currently traversing over 15 different sovereign countries every single hour.
Moving at 17,500 miles an hour.
Right. So who actually has the authority to knock on that server's door and demand the data? If the satellite happens to be flying through the thermosphere above France at the exact moment the subpoena is executed, does French law temporarily apply for those 3 minutes?
It creates a massive legal gray zone. The Morgan Lewis report emphasizes that there are currently no clear, tested international treaties governing cross-border data disputes in orbit. It is the Wild West of data management. Without absolute regulatory clarity, massive enterprises and financial institutions will be terrified to put their most sensitive data up there simply because they have no idea which judge in which country might successfully claim jurisdiction over it.
It's crazy to think about. We can solve the thermodynamics, we can build the reusable rockets, we can shield the chips from radiation, but the entire industry might get tripped up by an international subpoena.
It's a very real possibility.
So looking at the fragility of all these dependencies, where is this actually going? The strategic analysis lays out a roadmap to a $39 billion market by 2035, but it feels like walking a tightrope.
The roadmap is ambitious, for sure, but it relies on sequential breakthroughs. Right now, from 2025 to 2027, the industry is entirely focused on the proof of concept phase.
Right. We are seeing early, small-scale prototypes launching from companies like StarCloud, Axiom, and Orbit AI. I noted that Orbit AI is partnering with a company called PowerBank to test decentralized AI and blockchain verification in space.
Yeah, and the solitary goal of this current phase is to validate the core technology. They are trying to hit what aerospace engineers call technology readiness level 8 or 9.
Which means...
In plain English.
Yeah.
They need to prove it actually works in the brutal environment of space, not just in a vacuum chamber in a laboratory on Earth. Can they actively manage the heat without melting? Can they maintain the power draw?
Then, assuming they survive that, the projection moves to early commercialization from 2027 to 2031. This is when companies like Interflux, who are working on a wild concept called the Galactic Brain Project, using lasers to transmit power, aim to have actual commercial nodes operating.
Right.
This phase is heavily reliant on securing those anchor tenants we just discussed, defense agencies and major Earth observation companies.
And if the anchor tenants sign on, the period from 2031 to 2036 marks the rapid growth and capacity expansion phase. The ESA's Ascend project is targeting this exact window to launch a massive 50-kilowatt demonstrator, which would represent a monumental leap in orbital power management. And by 2035, the analysis projects the sector will reach a $39 billion market size.
The report mentions a compound annual growth rate of 67% to get there. Wait, 67%?
Yeah.
A 67% CAGR means the market size is practically doubling every single year during that sprint. That is explosive growth.
It is, but the report is explicitly clear that hitting that $39 billion mark is incredibly fragile. It relies on 4 foundational pillars, and if any single one of them fails, the entire market projection vanishes.
Those 4 dependencies are absolute, First, heavy lift launch costs must remain reliably and permanently under that $100 per kilogram threshold. If rocket companies raise prices, the economics fail.
Right. Second, the technology must mature beyond the lab. Thermal management, solar power generation, and fully autonomous operating systems all have to be flawlessly proven in orbit. Because you can't just send an IT technician to space to reboot a frozen server.
No, you definitely can't. Third, the international community must provide regulatory clarity. They have to resolve the legal chaos surrounding data sovereignty and implement enforceable space debris management protocols.
Yeah, that gray zone has to be eliminated to ease enterprise anxiety.
And fourth, they desperately need those anchor customers. They need massive, multi-year contracts from government agencies or tech giants to stabilize the early revenue while this incredibly expensive infrastructure is being built out.
It is a high-risk, high-reward strategic pivot for the entire global tech industry.
Definitely.
The conclusion of the strategic analysis summarizes the stakes perfectly, I think. Building orbital data centers is not just a novel way to host websites. It represents a definitive first step toward utilizing extraterrestrial resources to ensure humanity's sustainable technological growth.
It completely redefines the future of energy consumption, data security, and global geopolitics.
Exactly.
So let's recap what we unpacked for you today. We aren't talking about moving data centers to space just because it's a fun engineering challenge. It is a forced evolutionary leap. The explosive, heavy footprint of AI is pushing our earthly power grids, our construction timelines, and our water supplies to the absolute breaking point.
It's unsustainable.
Right. Space offers a lifeline. Infinite, zero-carbon solar energy and total physical isolation from terrestrial disasters. But to unlock that $39 billion frontier, engineers have to solve the unforgiving thermal physics of a vacuum, survive cosmic radiation and high-speed debris, and navigate a total legal free-for-all regarding who actually owns a piece of data floating in the thermosphere.
Which forces us to, since the invention of the telegraph, our global communication network, the internet, has been inextricably grounded in the physical reality of our planet. It relies on thousands of miles of cables buried deep in our oceans, massive server farms sitting on our land, drawing incredible amounts of power from our rivers and our coal seams.
Right.
But if the absolute core of our future artificial intelligence, our most critical data, and our vast processing power moves permanently into the vacuum of space, entirely detached from our biosphere, does humanity become a multiplanetary digital species before we even establish a physical colony on another world?
Wow.
What does it actually mean for Earth when its digital brain is no longer terrestrial?
If the server processing your next AI prompt is permanently gliding through the freezing vacuum of space, where does that leave us down here? That is a fascinating concept to chew on. Thank you for exploring this next frontier with us today on The Deep Dive. We'll see you next time.